Hi Ryan, can you hear me?
Yes, I can.
Ah, good. I can hear you. Okay. How you doing?
Um, I'm doing well. It's early though. Or earlier than like the past few days that I've gotten up.
Wow. Uh, oh, because yeah, yesterday was a holiday.
Yeah, and fr Friday I had off because the school is doing like a community service day, and seniors don't have to do that.
Oh,
Hmm. Yeah.
so you got
So
used
I
to.
had a long weekend.
Do you like to sleep in?
Yes, usually.
Typical
Still
teenager.
waiting on Walter over here at Canterbury.
Okay. Um, yeah, Walter said he might be late, so
Okay.
Okay.
what his story is. I had trouble getting into Adobe Connect today. I don't know why. Uh, It said
Okay.
it said my password is invalid for some reason, and I checked it, and then I said, okay, I forgot password, and it was supposed to send me an email, and it didn't send me an email, so I'm not sure what's happening. I don't think we need it because it's. Let me remember. Logan is doing what? I can't remember. He's doing something today.
I think he's at Rice today.
Oh, right.
Um,
College visit at Rice.
yeah.
Okay. Rice is in Houston.
Yes.
Yes. Yeah. My son got rejected from Rice, but he got into Yale. How's that for weird? Well, Rice is a good school. Very good school.
Yeah.
You can never tell. Where did you apply?
Um, I pl- uh, I played at St. John's in New York.
Right.
Um, I heard back from them. I got accepted, but I've all my other schools I've applied to, I haven't heard back from, like Pepperdine, UCLA, like uh, UCSB and UCSD. I haven't heard back from.
Uh-huh.
University of Texas, I haven't either, and uh, was there another one? I don't remember.
Okay, that's good.
Yeah, I've only heard back from one, so
Yeah. So you can hold off St. John's. Yeah.
yeah.
Okay, that sounds good. Okay. So, um, yeah, if it's early for you, well, I don't stay up so late, but I do have a rehearsal Monday night. It's a little.
Yeah.
Uh, um, so,
If it's earlier for you.
yeah, right. It's 9 o'clock. I set my alarm for 7, but I got up at 8. I think I'm not going to set my alarm for 7 anymore. Uh, let's see. Okay, conjectures. So, I haven't tried this myself. So let's see what happens. So did you try 3B on the?
3D, yes.
Yes.
Um,
Can you uh, can you share your screen on that and show me what you?
uh, yeah, let me pull up my document first.
Okay.
Uh, I sent it.
Yeah,
Here
you
it is.
sent it this morning.
Download. Oh, I'm not sure if I can present because
Oh,
I can't put myself as a presenter.
right. Okay, I'll pull it up.
I can
I'll pull it up and you can talk. That should work.
I can zoom in on my screen if you want.
Well, try whatever. Uh, just like I said, I couldn't get into Adobe Connect. Um, I tried twice. I mean, I can send an email to Nelson, but by the time he answers, although I could try to do that. I'm gonna see if there's something wrong with it. Because I didn't even get, usually when it says forget password, they send you a message,
Yeah.
and it didn't. So, okay, I'll send it quick. Let me just, while you're doing that, you try that, and I'll try this, and then.
Oh, okay, I went back through some emails. I guess Walter is participating in a problem-solving contest today at Trine.
Right,
He's been excused from classes here at Canterbury, so if he
right,
will be connecting, he'll be connecting on his own from there.
right. That's what he told us.
All right, I'll go ahead and disconnect from here and
Okay,
go
thanks.
do some
Son.
other stuff.
All right.
Take care.
Yeah, you too. Uh, okay. Adobe Connect problem. Oh yeah.
Let's see if it'll focus.
Yeah. All right. Well, we'll see what happens. Okay. Let me just finish sending this. I couldn't get into Adobe Connect today. It said I had an invalid password. I clicked that password. It didn't send the message. Just a link. So let me just send him the link, and then we'll do this. Okay. All righty. Okay. Yeah, I can see that. That works.
Okay, great. So I had the one where lines A, B were parallel,
Right.
and C was a transversal, basically.
Right.
So let me scoot around here so then I can see it.
Right.
So I basically said that. So I made a point F, and what I did to simplify it at the beginning.
Where? Point F is where?
It's right here.
Oh, a point F on line A.
Yes, point F on line A, but to simplify it, I also put point F where line A intersects with line C. Let me.
Okay.
Oh, whoops.
Okay, so line C is the which one is line C?
Oh, in this image, it doesn't show that I put the line on, or the point F on line C. So line C is right here.
The bottom one.
It's the bottom one.
Okay.
And
okay, so you put F at the intersection of A and C.
Yes, when I was trying to figure out at the very beginning, but in this image, I didn't do it.
Okay.
So what I did find, or what I thought I found, was that the translation vector is parallel to line C. And
what is it? Is it a glide reflection?
Yes, we're trying to show that these are glide reflections.
Okay.
Yeah.
And the translation vector is parallel to line C. Okay.
And what I did to define the distance of, or not define, but show the distance of the, or the magnitude of the translation vector was, what did I do? Can I read through this?
Yeah. You know what? I think it's better if I get it up. I'm going to share my screen and get it up, and then you can tell me, and then you can look at it. That makes more sense. So
okay.
Let me do this. And which screen am I sharing? I'm going to share this screen, the Blue Jeans screen. Oh no, I can share the other screen. Okay. Yeah, I can share this screen, and so I can still see you. Okay, so I'm going to share this screen, and then I am going to get up. So that's you're looking at your Is it one of the ones you sent me? I'm looking at. You sent me a
Yes.
Paragal dissection GeoGebra, but so this is in the reflections. I see. It's a Word doc. Got it.
Mhm. And I included some pictures of my.
Got it. Okay. So I'm gonna open that. Okay. So we go into homework. Okay. Here it is, and it's the there it is. No. Wrong one. Sorry. 217 homework, and then there's. Oh, I thought I had. Well, I thought I had put your homework in there, and I didn't. Put it somewhere else? No, I don't know where I put it. Gosh. Okay. Well, I have the email. I can open it from there. Yeah. So it's well, let me do this again. This was funny. I saved them all, I thought, and I'm going to need to do that. So save these attachments, and I go into 17 is it's the wrong. This is 213 homework.
Yeah.
There it is. Okay, I went in the wrong. That's why.
It's all good.
Got it. Okay. So I confused myself very well there. All right. So we're going to get this right now. Okay. So 213 homework. There's Ryan's homework. There it is. Okay. So this is the 6. Yeah, this one right here. All right. Can you see that?
No.
Oh, you can't see this screen?
No, but I can see my screen, which will be fine.
Oh, true.
I can explain to you.
Yeah, okay, sounds good. Okay, so now I have your picture. Okay, go ahead.
F is on line A, and so when you reflect across A, it'll be the same point. So F and F prime are the same point, and then you can see F double prime reflected across, or is the reflection of F prime over B, and then F triple prime is the reflection of F double prime over C.
Got it.
So, what I was thinking, after I thought it through, I realized that you could go about it two ways.
Mm-hmm.
The first way, I don't think I mentioned this in the
In the
this yeah, but so the line of reflection will be parallel to C.
Okay.
And that is shown by line R. It's the red line.
Got it.
And I found that by let me first tell you what D is, or line D is. Line D is just a line that's perpendicular to line C that runs through not runs through, but includes F triple prime. And then I also did a line E, which is purple.
Mm-hmm. Mm-hmm.
And that is parallel to line C as well.
Mm-hmm.
And it includes point F.
Mm.
So when I move F, E moves along with it. And,
okay.
So where D or line D and E intersect, there's G, and that's point G and point F. That is the distance of the magnitude of the translation vector. That will be. That's what I found, and it will be. And that translation vector will also be parallel to
the line of reflection.
Yes, and in turn C and E.
Okay, so F.
And another thing to mention is that the reflection line, the red one, is halfway in between point G and F triple prime.
Yes.
It's a perpendicular bisector. That line, yeah,
Right.
it's a perpendicular bisector of segment G F triple prime.
Right.
And at the beginning, I was having trouble defining the distances because I didn't know the magnitude of the translation vector.
Mm-hmm.
Because I didn't have point G to start out with.
Mm-hmm.
So I had to define that, or I had to, not define it, but I had to prove that those lines existed, or that you could make those lines, and then that point would also exist. And then it's a very crucial point.
Right, good. Okay, so let me run through this in my mind and just talk it through. So, okay, so F goes to, so you translate F to G, and then, which is, let's see, C is the other line. That's right. So that's a line through F, parallel to C. And then, so you translate along that line until you get to D, which is...
Which picture are you looking at? Are you looking at the first or the second one?
First one.
Okay. Yeah. Yeah.
Okay. Is there, so the second one does what? There's a second picture, and
that one is me trying to prove that that would actually work.
Yeah.
And,
okay.
What I suggested would work because what I was thinking at this point, this looked a lot like your fundamental theorem of dilations.
Uh-huh.
So it was at this point that I actually realized that you could actually switch. You could, instead of translating parallel to what is it? Line C.
Yeah.
You can actually go in the not perpendicular to it.
Okay, so run through the second picture for me.
The second picture, I just this is where I actually overlap, or I superimpose F onto both line C and A, so where they intersect, and that's point F prime, and E.
Yeah.
And that's when I set up similar triangles. And I don't think I proved it completely, but yeah, I wasn't sure where to go from there.
Okay, I see. Good. Okay, good. So you say, to prove this, I will prove that it's similar, but then, okay. So the key, what I see, I mean, I'll look at this more carefully and make some comments, but what I see is, one has to define the glide reflection. I'm getting an echo. Are you getting an echo?
A little bit. That might just be on my side.
All right. It seems better when I'm not so close. So I'll try this. One has to define the glide reflection without reference to the initial point. That's the crucial. That's the crucial. You can never. I made that comment last time that it can't involve the pre-image point or the image point. So for example, in number one, in number one, which was 3 parallel lines, we had to say it's a reflection, and we told how to locate the reflection line just using the given lines A, B, and C. it didn't have, the idea was you start at A, you start at line A, and you translate perpendicular to A through the distance between B and C, from B to C, that vector. And
Okay.
that defined the line. And that did not involve a pre-image point,
Okay, yeah.
right? So that's a crucial point here. So eventually that's what you want. You want something that's independent of the point.
Okay, yeah.
Okay? So I'm not sure that you've done that yet. Is that correct? What you've done?
No.
Yeah. Okay. That was a very good first start, and it was well explained.
Sorry. I get a little over. I don't know. I try to explain it a little too much, but
I see. Yeah.
yeah, I'm not very good at explaining things, but it'll come in time.
Yeah, absolutely. Good. Thank you. I'm glad you said that. That's it takes a lot of practice. I'm an old guy. Been doing it a long time. And yeah, the more practice you get. And then the other thing is a little quote from George Palya, who was some consider him the founder of problem solving. He wrote a book called How to Solve It. He was a mathematician at Stanford, but he also was very interested in heuristics or pedagogy or teaching, that kind of thing. And he said, it's not a problem if you can do it in less than 24 hours. So, good. Okay. So keep thinking about that. And I will too. And that's good. Okay. So I'm going to close this. I'm surprised that you couldn't. Yeah, it still says share screen, and why nothing's working well today. I'm going to try this again. It looks like the right screen. Looks like I have the right screen. Oh, no, now I'm clicking on it. Maybe that's better. I don't know. So I'm going to try share screen again. It doesn't seem to be doing much. Can you see anything? No.
In Adobe?
No, in Blue Jeans, because I'm trying to share it.
No, nothing's coming up where it usually shows.
Okay. All right. It's kind of annoying. All right, that's all right. Well, we'll do it this way. Okay, so now I want to go to the symmetry definitions and proofs. And and I wanted to show you Walter's. Well, that's all right. Walter had an interesting proof of the lemma, but let's get up that first. The symmetry definitions and proofs, which you also turned in.
I'm not sure I did it right.
Okay, let me get it up. Let me get it up. Yeah, here it is. Okay.
With your example for how to do the proof.
Yeah.
On this one, does your proof start after when you say, or does your proof start when you start putting in the images, or all of that's the including like the lemmas and corollaries? Is that part of your proof?
The lemma, it's called a lemma, and it is part of the proof, because a lemma is a helping theorem needed for the main proof.
Okay, I did not include those. I'll go back and try to do it.
Okay, hold on. Let's go through 6 first. So the lemma, the first lemma is that any isometry preserves collinearity and betweenness. And we're assuming that isometries preserve angle measure. And in fact, all all we really have to assume is that reflection, ultimately, when we prove this stuff, is that reflections preserve angle measure because any isometry is made up of reflections. That's basically the 1, 2, or 3 reflections, that you can get any isometry in 1, 2, or 3 reflections. So all we really need to assume is that reflections preserve angle measures. And given that, then if you have collinear points, then the middle one, you can get a straight angle, and it's going to be a straight angle in the image too. So that proves that collinearity and betweenness are preserved.
Okay.
Okay. And then
so the proof after lemma 1 is proving lemma 1.
Yes.
Right? Okay.
Yes. That was the difficulty. Got it. Yes. So one states a lemma, and then the proof of the lemma, and then another lemma, and then the proof of the lemma, and then the proof of the main theorem.
Okay, and you can have as many lemmas as you want, right?
Yes.
Or as you need.
Yes, exactly.
Okay.
Okay. I'm glad you asked that. That's an important point. Okay. So, all right. And then the second lemma is that the image of a line L in a half turn with a point not on the line is parallel. And the diagram kind of shows it, because if you rotate 180 degrees and then the segment PQ will, the image of that will be on the same line because it's a straight angle rotation. So QP, Q prime are collinear, and so they make it transversal. And since it preserves angles, the alternate interior angles are equal.
Okay.
And so since the alternate interior angles are equal, the lines are parallel.
Oh, okay.
Does that make sense?
Mm-hmm.
Now, Walter had a very clever other proof, which I thought was interesting, and that was, suppose they weren't parallel, then they would meet somewhere, and that point would be a fixed point of the rotation. Because, let's see why. Yes, because one line. Let me think about that. I thought that was obvious, but maybe it's not. If they met somewhere, then that point is on the first line, and then when you rotate, you get a point on the second line, but maybe it doesn't have to be that same point. So now I'm not so sure. I thought it was really clever at first, but now I'm not so sure. So anyway, I have to think about that some more. But anyway, the proof I just went through for you works. Okay. All right. So those, and that's an important thing that comes up a lot. So those are the lemmas, and then this proof down here is the proof of the main theorem, and the main theorem is a way of proving that if we have our traditional definition of a parallelogram, namely opposite sides parallel, then the quadrilateral is a parallelogram under the symmetry definition. That is, it has 180 degree or twofold rotational symmetry.
Okay. Yeah.
Okay. So, because going the other way is easy, is much easier. Okay. So if opposites are there, there's the theorem. So we restate the theorem, and then we have a proof. And this proof is actually Henry wrote this one up, my colleague. Given a quadrilateral ABCD as in the figure, we'd like to prove that it has 180-degree rotational symmetry. Okay, clear on that?
Yeah.
So there it is, and we have parallel. We're given parallels. So on the next page, we locate the center of the rotation that we're talking about, and we do that by drawing a diagonal and getting the midpoint. So M is the midpoint, and then consider H. He just calls H the half turn with center M. Okay, so we need to show that that the parallelogram goes into itself. So since M is the midpoint of AC, C is the image of A in that half turn. So when we do a half turn around M, then it's going to make a straight angle. And since the distances are equal and it preserves distance, C is going to go into A.
Yeah. Okay.
And A is going to go into C.
Okay.
Verse. Okay. So C is the image of A. Okay. And then by lemma 2 and the parallel postulate, lemma 2 was that 180-degree rotation maps a line into a parallel line if the point's not on the line. So by lemma 2 and the parallel postulate, the image of line N, which is this line here through A and D, the image of N is going to be is L, and the image of line, okay. So the image of line N is going to be parallel. The image of line N is going to be parallel to N, right? And it's going to go through C because we said A goes into C.
Yeah, okay.
So it has to be line L. It has to be line BC because that's the parallel line that goes through C. There's only one of them.
Yeah.
Okay? And similarly, and then the image of line K has to be M for the same reason, because K goes through A, and 180-degree rotation is going to take that line into a parallel line, but A goes into C, so the parallel line has to go through C.
Okay, yeah.
So that means that the image of K is M. So the image of N is L, and the image of K is M. Okay? And that's uniquely determined. But B is the intersection of K. Yeah, let's read this. So B is the intersection of K and L, and therefore is the image of the intersection of lines M and N. So in other words, take point D, which is the intersection of lines M and N, and if we rotate 180 degrees, then line M is going to go into line K, and line N is going to go into line L. So the intersection D, which is the intersection of M and N, is going to go into the intersection of K and L, and that's B.
Okay.
So D has to go into B, and B goes into D. So that proves that the parallelogram gets mapped onto itself by this half turn.
Okay. That makes sense.
Okay, good. So that's it. It's not so easy, but that's the proof. Okay, now here's your turn. So you chose a theorem, and your theorem is, I shouldn't have said working with a partner. This was made originally, I didn't change it anyway. It was made for teaching teachers. But anyway, so tell me what you're doing here.
So I was trying to prove the theorem that if a quadrilateral has all its sides the same length and opposite sides are parallel, or when I wanted, would that be too much to prove in a theorem?
Yeah, I think that's too strong.
Okay.
Did you look at the theorem list that I made? It's under the references.
I think I did. Let me check.
Yeah, it's in eCollege under the TransGeo references.
Okay. And,
Why don't you look at that?
yeah.
It's at the end of that document. Oh, Walter's coming in.
We're supposed to choose from all these.
Hi, Walter.
Oh, hi.
How you doing? How's your problem-solving contest? Or you're still working on it?
This weekend I was at Yale and my flight got canceled, so I wasn't actually able to go.
Oh, I'm sorry.
Yeah.
Was the weather bad? And you were supposed to go where? You were supposed to go to what city?
My flight from Hartford, Connecticut. Wait, no, my flight from Chicago to Fort Wayne was canceled.
Oh,
So, I had to spend the night in Chicago.
oh, I see. So you had gone. Where had you gone? You've gone to Connecticut.
I was at Yale.
Oh, you were at Yale. Okay, so you were visiting Yale. My son went to Yale, and his wife. Well, his wife did too. That's where they met. Okay, so you had trouble getting back. I see. You had trouble getting back for your contest. So when did you get back?
Like 15 minutes ago.
I see. Okay. Wow. Okay, so let me quickly fill you in on. First of all, I had trouble getting into Adobe Connect today, and I'm not sure why, but I did. So what Ryan and I did first was go over his. I'm getting a little echo. Is that all right? It's all right. What we did first was to go over the three reflections, number three, part of number three that he did, and he had an interesting way of constructing things, but it depended on the initial point, and that's a really important point, that the final isometry has to just depend on what you're given, the three lines. Okay.
What?
Can you hear me?
Yeah, I can hear you.
Okay. Did that make sense?
Yeah, that makes sense.
Okay. Have you had a chance to try yours yet?
No, I was busy the entire weekend.
Okay. So anyway, so that's an important point. So when you try it, try to make whatever your definition or your specifications for the isometry has to not depend on the initial point. It has to just depend on the given lines. Okay?
Okay.
Okay. All right. So we went through that.
Mhm.
And now we're on the symmetry definitions and proofs. And I went through number 6, which was the proof that if opposite sides of a quadrilateral are parallel, the quadrilateral is a parallelogram. On that sheet.
Okay.
And
Yeah.
I just went through the proof with Ryan, because he had a little difficulty realizing that the proof of the lemma. So you have a lemma, and then the proof of the lemma, and then a corollary, and then proof of lemma 2 is the proof of lemma 2, and then you have the theorem and its proof. But anyway, we got through that, and then Ryan was explaining to me his theorem. But Ryan,
Yes.
you need to state your theorem. So when you come back to this, okay, you need to start off with a statement of what you're trying to prove.
Okay.
Okay. So start off with that, and he's trying to prove that, and the theorems that you should select, Walter, come from that theorem list. So that you realize that.
Okay.
Okay. So I stated, four theorems for each quadrilateral, and just pick one. So Ryan, I think, tried to over-determine it a little bit. So you want to pick either a quadrilateral that has all sides equal is a rhombus. That is has and our definition of a rhombus was, let's see, was what kind of symmetry? It was
two lines of symmetry through
That's by
vertices.
going through vertices. Right. So you want to prove that if all sides are equal, then it has 2 lines of symmetry going through vertices. Or what else? Or something like that. I mean, any of those theorems on that list. Okay.
Yeah.
All right. So when you did something, did it? You know what? Let's not spend time on this. I will look at what you did and make some comments. Okay, Ryan.
I'll send in a new one.
Okay.
Yeah.
Okay. Sounds good. Okay. So now, I wanted to go through 1 through 4 of Paragal. And it's a little hard because we can't share our screens today. But I'll get up so you guys should all get up that file, and we'll just talk about it. So it's Paragal's dissection of geometric justification of Pythagorean theorem. And there any questions about 1, 2, or 3? I don't think so. Those are, no, number 3 is important. So the opposite sides of this special quadrilateral are what?
It's. Do you want me to say the equation?
Yeah.
It's A plus B equals E.
A plus
Or D, I mean D, sorry.
B. A plus B equals. Wait a second.
A plus. Let me. I said it wrong.
Let me get yours up. Let me get yours up. I got the wrong one up. Let me get yours up. Here it is. Okay. There we go. All right. So I will see what you said. The opposite sides are equal and parallel. That's true. And A plus B equals E. That's correct. Yes. because the opposite sides are equal. So we know that A plus D equals E. And then you were supposed to, number 4 was to use the file as a start, complete the diagram to the right by making polygons for the square on the shorter leg and the 4 pieces. So I'm going to get up, Ryan, I'm going to get up your GeoGebra sketch and see and take a look at it. So give me a second. So this is 213 homework. There it is. No, it isn't. Ryan's. Let's do it right. There it is. Okay, RP. All right. Okay. Okay. Interesting. So Ryan, what you did was you seem to have successfully made the 4 pieces of the large square CFGB.
Mm-hmm.
You don't want to make 4 pieces of the small square.
Oh.
You don't want to do that.
Do I want to make more?
No, you want to make none. So the idea is that just the small square and the 4 pieces of the large square will fit into the square on the hypotenuse, the bottom square.
Okay. Whoops.
Okay. So you can, but you did it correctly. You made those 4 pieces correctly. How did you locate the center? Let me ask you that. The center of square CFGB.
I got the midpoints for each side.
Mm-hmm.
I guess you can just do a midpoint for I got a midpoint for CF or segment CF, and then a midpoint for segment CB.
Uh-huh.
And I use the parallel line tool to do it for either one, or for both of them, and then I put one of the lines onto the midpoints.
Okay.
Okay. Yeah. Where they intersect.
Can you think of an easier way to locate the center of a square? Walter, what's an easier way to locate the center of a square?
Isn't it just intersection of the diagonals?
Yeah, you can intersect the diagonals, or you can take the midpoint of one diagonal. Okay, Ryan? That's easy. But that's right. So once you locate the center, then you just want to make a line perpendicular to the hypotenuse AB, right? That's probably what you did, or parallel, perpendicular, parallel, and that gives you the two lines that you want. Okay, so the idea was just to get through 1 through 4 on that today. Okay, so now you've got the idea, and the homework will continue to use this sketch, and I'm going to want you to actually move those pieces into place and then show that they really fit. That's Paragal's dissection. It's like a puzzle that you really can take pieces from the 2 squares and put them into the large square. And they fit and everything works, which is really kind of neat. Okay. All right.
Mr. Douglas?
Yes.
I'm sort of confused as to what number 4 wants me to do.
What number 4 wants you to do is to make that diagram. So let me go back to. I'm glad you asked that. So I put up a sketch which has the right triangle with its hypotenuse horizontal on the bottom, and the squares on the legs and the hypotenuse. And all it wants you to do is to make the 4 pieces. So I want you to make those lines in the large square.
Oh, okay.
Through the center.
Like the dotted lines?
Like the dotted lines, exactly.
Okay.
That's just make those. That's all. And then I just want to make sure that was right, and I'm glad I did because Ryan, made more that were not necessary. So, and then you're going to have 5 pieces here, and you're going to move these 5 pieces into place in the large square. That's what the next step is going to be. Figure out how to move those, how to translate them, actually, just a translation. How to translate them into place so that they fill the square on the hypotenuse.
What are the 5 pieces?
The 5 pieces are the 4 pieces of that we've broken the square on the longer hypotenuse into, and the square on the shorter, on the longer leg, and the square on the shorter leg.
I see. Okay.
Okay. Good. Those are the 5 pieces. All right. So we did that. Now I am going to get up a new file. So we got 10 minutes, and I'm going to run you through some of this. And so there is a file that is in eCollege. So you guys should. It's under the class, today's class, 217 class, and it says. Let me get to the right place here. Yeah, 217 class. And one of the files in there says transforming graphs, advanced math topics, transforming graphs. So if you could get that up, since I can't share my screen, just get that up, if you would. Should be in eCollege. I'm pretty sure I put it there.
Under February 17th?
Yeah, 217 class files. No?
It only goes up to February 13th.
Boy, I put it in there. All right. For now, easiest thing for me to do is send it to you quickly. So let me do that. Let me wait. Hold on a second. Let me look at eCollege because I know I put it in there.
It's not there.
Not there. So there was something happened over the weekend. That's why it's not working. So what I need to do is send you these files to make sure you have them for now. So let me do that. Okay, I'll send you all of you. So Walter and Ryan. So February 17 class files. 17 class files. Yeah, I'm glad we found this out. So I'm going to say attached. Okay, attach them now. 217 class. Okay. Choose. Okay. I'm sending it now. Oh, wait a minute. I did the wrong one. I think. Maybe not. No, I'm just looking at the wrong one. Let me see what I sent. Make sure it's right. Oh, it is right. Yes. Well, that's 4 files, and one of them is called Transforming Graphs. The last one.
I got it.
Yeah, I got it.
Okay. So, okay. So, this is readable, I think, but let me at least spend the rest of the time, 5 minutes, just going through the first part of it. So now we're going on to the next topic, and the next topic was we're going to do quickly transforming graphs. And when you look at when you think about transforming graphs from a transformational point of view, you get some unity that you probably didn't get when you learned it in high school. Whichever course you learned it in. So the first part is inverse transformation. So since the geometric transformation is a one-to-one mapping of the plane onto itself, every transformation has an inverse. Okay? So here are some exercises, some quick exercises. If t of xy equals x plus 2 comma y, in other words, we move the x coordinate, we add 2 to the x coordinate, then the inverse is going to subtract 2 from the x coordinate. Okay?
Okay.
All right. Now, here's what I want you to think about. Can you find the inverse of this one that multiplies the x coordinate by 3 and then adds 2 to it?
Would it just be x minus 2 or x divided by 3 minus 2?
Try that with a number. If you have some scratch paper, Brian, try that with a number.
Yeah.
Walter, what do you think it is?
Yeah, isn't it x minus 2 over 3?
Yes, it is.
Yeah.
Do you see why that doesn't work? It doesn't work because of shoes and socks. What do I mean by that?
Order of operation.
Yeah. So in other words, when you get dressed in the morning, you put your shoes on first, and then you put your socks on first if you're a normal person, and then your shoes. When you get undressed at night, it's your shoes that get taken off first, and then your socks. So it reverses when you go backwards. So the same thing happens in general here. That's what number 2 says. If U is S followed by T, S followed by T, then the inverse is going to be what?
S followed by U?
No. If U is S followed by T, which is, think of S as your socks and then T your shoes.
Oh, would it be S followed by UT?
No.
Oh,
Yeah,
isn't it S inverse followed by T inverse? Wait, no, you first apply T inverse and then you apply S inverse.
That's right. It's T inverse first and then S inverse.
Okay.
Because if U is first you do S, then you do T, then to undo that, you undo T first, the last thing you did, and then you undo S.
Okay.
So shoes and socks, put your socks on, then you put your shoes on. To reverse that, you first undo putting your shoes on, which was the second thing you did, right? And then you undo putting your socks on.
Okay.
All right?
Uh-huh.
So it reverses it. That's important. All right. So now we're out of time. But this next argument is a general argument for, so I'll just say this one thing. So we have this f of xy equals 0, and that's just for notational convenience because the equation doesn't have to be solved for y. It can be any equation involving x and y, any relation. Doesn't even have to be a function involving x and y. And in order to find, and then we use some transformation to get some new graph. And we want to find the equation of the new graph. To find the equation, we can pick a point on the new graph, which is xy. You pick a point on the new graph, pull it back by the inverse transformation into a point on the old graph, and then that point on the old graph satisfies the old equation. So that's how we can get an equation for the new graph. And that is a general idea that works for anything. So you have to think about that for a little bit, but after that I gave you an example. You can read through the example carefully and the useful transformations, and then I'm going to assign you exercises 1, 2, and 3 for homework. Okay?
Okay.
If you have any questions, send me an email. Or we can get together or whatever. And I'll figure out what's going wrong, what went wrong with the Stanford site over the weekend, because I did post those things. All right, so we're out of time. Walter, welcome home. Glad you got back.
Yeah.
I'm sorry you missed your problem solving contest. Okay,
Yeah.
guys, we'll see ya.
Thanks.
See you on Friday. Take care.
Right.